Welcome to this coding walkthrough. Today, we're tackling LeetCode problem number 435, titled Non-Overlapping Intervals. This problem challenges us to find the minimum number of intervals to remove in order to make the rest non-overlapping. It's a fantastic question to strengthen your understanding of greedy algorithms and interval scheduling. Let's dive in. In this problem, you are given an array of intervals where each interval is defined by a start and an end value. Your task is to determine the minimum number of intervals you need to remove so that the remaining intervals are non-overlapping. For two intervals to be non-overlapping, one must end before the other begins. This means if you have an interval, a, b, and another interval, c, d, they will not overlap if either b is less than or equal to c, or d is less than or equal to a. The input consists of a list of intervals represented as a 2D array, where each subarray contains two integers, the start and end of that interval. The output will be a single integer, which represents the minimum number of intervals you need to remove to make sure the rest of the intervals do not overlap. For example, if the input intervals are 1, 2, 2, 3, 3, 4, 1, 3, the output will be 1. This is because we can remove the interval 1, 3, and the remaining intervals 1, 2, 2, 3, 3, 4 will no longer overlap. In another example, if the input intervals are 1, 2, 1, 2, 1, 2, the output is 2. In this case, we need to remove two intervals to leave just one interval, such as 1, 2, in order to make the set non-overlapping. The goal is to minimize the number of removals required to achieve this. As another example, consider the input intervals 1, 2, 2, 3. Here, the output is 0 because no intervals need to be removed, they are already non-overlapping. The constraints for this problem specify that the input list will have at least one interval and at most 100,000 intervals. This means that the solution must be efficient, ideally with a time complexity of O, n log n, or better. Additionally, each interval consists of exactly two integers, representing the start and end points, where the start point is strictly less than the end point, ensuring well-formed intervals. The range of values for the start and end points of the intervals is from -50,000 to 50,000. Meaning the intervals can span both negative and positive values. Your solution should account for this range and handle it properly. Some edge cases to keep in mind include scenarios where there is only a single interval, as no removals are needed in that case, and situations where the intervals provided are already non-overlapping. You should also ensure your solution is efficient enough to handle the upper limits of the constraints, such as when the input size approaches 100,000. Additionally, consider cases where intervals overlap at the same start or end points, as these can be tricky edge cases that need careful handling. To solve the problem of making intervals non-overlapping, we first consider the brute force approach. The intuition here is straightforward but computationally expensive. We generate all possible subsets of the given intervals and identify the largest subset where no intervals overlap. The intervals not in this subset are the ones we would remove. To determine if a subset is non-overlapping, we compare every pair of intervals within it. However, the computational cost of this method quickly becomes prohibitive. Generating all subsets requires O(2 to the power of n) operations, and verifying overlaps within each subset adds an additional O(n²) complexity. As a result, this approach has an overall exponential time complexity, making it impractical for larger input sizes. While it helps us understand the problem, we need a more efficient solution for real-world use cases. A more efficient solution is the optimized greedy approach. The key idea here is to minimize the number of intervals we remove by prioritizing intervals with the smallest ending times. Why focus on the end time? Because choosing intervals that end earlier leaves more room for subsequent intervals, reducing the likelihood of overlap. To implement this strategy, we first sort all intervals based on their end times. Then, we iterate through the sorted list while maintaining the end time of the last included interval. If the start of the current interval is earlier than this end time, it overlaps and needs to be removed. Otherwise, we update the end time to the current interval's end. This approach involves sorting the intervals, which takes O(n log n), and a single pass through the list, which takes O(n). As a result, the overall complexity is O(n log n), making this approach both efficient and scalable for large input sizes. Another potential solution is the dynamic programming approach, which provides a structured way to solve the problem but is less efficient than the greedy method. Here, we aim to find the largest subset of non-overlapping intervals using a method similar to the longest increasing subsequence problem. First, we sort the intervals by their start times. Then, we define a DP array where each entry, DP I, represents the size of the largest non-overlapping subset ending at interval I. To compute DP I, we check all previous intervals, and if one ends before the current interval starts, we update DP I as the maximum of its current value in DP j plus 1. The total number of intervals minus the maximum value in the DP array gives us the number of intervals to remove. This method has a time complexity of O(n) squared, due to the pairwise comparisons, making it slower than the greedy approach. While it's more structured and extensible, the additional complexity makes it less practical for this problem. The greedy approach stands out as the optimal solution for this problem due to its simplicity, efficiency, and effectiveness. The core insight is that minimizing the end time of the current interval reduces the likelihood of future overlaps, allowing us to retain the maximum number of intervals. By always choosing the interval with the earliest end time, we make the best local decision, which leads to a globally optimal result. While sorting the intervals adds an O(n log n) overhead, this cost is manageable and ensures scalability. Although the dynamic programming approach may be comparable for very small inputs, it introduces unnecessary complexity and slower performance for larger datasets. Additionally, while DP might be useful for problems with added constraints, such as weighted intervals, those extensions are not relevant here. In conclusion, the greedy approach strikes the perfect balance between simplicity and efficiency, making it the ideal choice for solving problem number 435. In this problem, we are tasked with determining the minimum number of intervals that need to be removed to ensure that the remaining intervals do not overlap. Each interval is represented as a range, start to end, where the start point is strictly less than the end point. To solve this efficiently, we use a greedy algorithm. The core idea is to always prioritize intervals that end the earliest, as this strategy maximizes the available space for subsequent intervals and minimizes overlaps. The first step is to sort the intervals by their end times. This ensures that we always consider the interval that finishes first, which is key to making optimal decisions. Sorting the intervals has a time complexity of O(n asterisk log n), where n is the number of intervals. Once sorted, we initialize two variables, prev_end, which tracks the end time of the last non-overlapping interval, and removals, which counts the number of intervals we need to eliminate. Initially, prev_end is set to -infinity because no interval has been selected yet, and removal starts at 0 since no intervals have been removed at this point. Now we iterate through the sorted list of intervals. For each interval, start to end, we first check if it overlaps with the previously selected interval. This is done by comparing the current interval's start time with prev_end. If start is less than prev_end, it means there is an overlap, so we increment the removals counter and skip updating prev_end to reflect that this interval is being removed. On the other hand, if there is no overlap, meaning start is greater than or equal to prev_end, we update prev_end to the end time of the current interval. This signifies that we have included this interval in our non-overlapping set. Once all intervals have been processed, the removals counter will hold the minimum number of intervals that need to be eliminated to achieve a non-overlapping set. The critical insight here is that sorting by end time ensures we always pick the interval that finishes the earliest, which leaves the most room for subsequent non-overlapping intervals. This greedy strategy guarantees that we minimize the number of removals. There are a few edge cases to consider for this problem. If the input list of intervals is empty, we simply return 0 because there are no intervals to process or remove. Similarly, if there is only one interval, the result is also 0, as there is nothing to overlap with. For cases where all intervals overlap with one another, the algorithm will correctly determine that all but one interval must be removed. In terms of data structures, we represent the input intervals as a list of lists or tuples, such as 1, 3, 2, 4, 3, 5. The intervals are sorted by their end times using Python's built-in sorting function and a lambda function as the key. Additionally, we use two simple integer variables, prev_end and removals, to track the end time of the last selected interval and the number of removed intervals, respectively. The code implementation follows these steps precisely. First, we sort the intervals by their n times. Next, we initialize prev_n to negative infinity and removals to 0. Finally, we iterate through each interval, checking for overlaps and updating the variables accordingly. In the final part of the implementation, when we encounter a non-overlapping interval, we update prev_n to the end time of the current interval. This update ensures that we continue to track the most recent non-overlapping interval as we move forward. After processing all the intervals, we return the value of removals, which represents the minimum number of intervals that need to be eliminated. When analyzing the algorithm's complexity, the time complexity is dominated by the sorting step, which is O n asterisk log n, and the iteration step, which is O n. Therefore, the overall time complexity is O n asterisk log n. The space complexity is O n for the input storage, but the sorting is done in place, requiring only O1 additional space. Thus, the total space complexity is O n. This makes the algorithm both time and space efficient for this problem. The provided solution to LeetCode problem number 435, non-overlapping intervals, uses a greedy algorithm. The goal is to determine the minimum number of intervals to remove so that the rest do not overlap. Explanation. 1. Sorting intervals asterisk. The intervals are first sorted by their ending times using the sort function and a key of x, 1. Sorting by end times ensures that we prioritize intervals with the earliest possible end. This is crucial for the greedy strategy, as it allows us to maximize the number of non-overlapping intervals. 2. Initialization asterisk. Two variables are initialized. Prev_n is set to negative infinity to represent the end time of the last included interval. Initially, there is no interval. Removal_count is set to 0 to track the number of intervals removed. 3. Iterating through intervals asterisk. The code iterates through each interval, start, end, in the sorted list. If the current interval start is less than prev_end, it means the interval overlaps with the previous one. Therefore, the removal_count is increment to remove the overlapping interval. If there is no overlap, the current interval is included, and prev_end is updated to the current interval's end. 4. Returning the result asterisk. After processing all intervals, the removal_count contains the minimum number of intervals that need to be removed to eliminate all overlaps. Complexity analysis. Time complexity asterisk sorting the intervals takes O n log n, and iterating through the intervals takes O n. Overall, the time complexity is O n log n. Space complexity asterisk the algorithm uses O1 extra space, as the sorting is done in place, and no additional data structures are used. Edge cases. If the input list is empty, the function handles it by returning 0, as there are no intervals to process. If all intervals are already non-overlapping, the function correctly returns 0. This solution is efficient and works well within the constraints of the problem. Here, we start by importing the necessary libraries and defining the solution class. The main method we implement is erase overlap intervals, which takes a 2D array of intervals as its input. The first step in solving this problem is to sort the intervals based on their ending times. This is done using arrays.sort with a custom comparator that compares the second element of each interval. Sorting by the end times ensures that we always consider the interval that finishes the earliest, which is key to minimizing overlap. Next, we initialize two variables. The first is prevend, which keeps track of the end time of the last non-overlapping interval we've included. Initially, we set it to integer.min_value to ensure it doesn't interfere with the first comparison. The second variable, removal count, keeps track of the number of intervals we need to remove. It starts at 0. After setting up, we iterate through each interval in the sorted list. For every interval, we extract its start and end times. We then check if the current interval overlaps with the previous one by comparing its start time with prevend. If it does overlap, we increment removal count, as this interval cannot be included. Otherwise, we update prevend to the end time of the current interval, as it's now part of our non-overlapping selection. Finally, the method concludes by returning the removal count variable, which represents the total number of intervals that need to be removed to eliminate all overlaps. This approach ensures that we maximize the number of non-overlapping intervals while maintaining efficiency, as sorting takes O, n log n, and the single loop through the intervals takes O, n. Together, the algorithm runs in O, n log n, time, making it well-suited for handling large input sizes. The concise structure of the code also makes it easy to follow and maintain. To solve problem number 435, non-overlapping intervals, the goal is to remove the minimum number of intervals so that the remaining ones do not overlap. Each interval is defined by a start and end time, and we aim to identify overlaps in the most efficient way. The approach begins by sorting the intervals based on their ending times. This helps prioritize intervals that finish earlier, leaving more room for subsequent ones. Let's consider the example input 1, 2, 2, 3, 3, 4, 1, 3. After sorting by end time, the intervals become 1, 2, 1, 3, 2, 3, 3, 4. We then initialize two key variables, preb_end, starting at -infinity to track the end time of the last included interval, and removal_count, which starts at 0 to keep track of how many intervals are removed. As we iterate through the intervals, we check for overlaps. For instance, the first interval, 1, 2, has a start time greater than or equal to preb_end, so there's no overlap, and we update preb_end to 2. However, the next interval, 1, 3, starts before 2, meaning an overlap occurs, and we increment removal_count to 1. This process continues for each interval, updating preb_end or removal_count as needed. By the end, only one interval needs to be removed, giving us a final output of removal_count equals 1. Now, let's look at a second example, 1, 2, 1, 2, 1, 2. Here, all intervals are identical, starting and ending at the same times. After sorting, the list remains as 1, 2, 1, 2, 1, 2. We initialize preb_end to -infinity and removal_count to 0. As we iterate through the intervals, the first interval, 1, 2, does not overlap with preb_end, so we update preb_end to 2. The next interval, 1, 2, however, starts before the updated preb_end, indicating an overlap. We increment removal_count to 1 but leave preb_end unchanged since we're removing the overlapping interval. Similarly, the third interval, 1, 2, also starts before preb_end, leading to another overlap. This increments removal_count to 2. At the end of the iteration, we find that two intervals need to be removed to ensure no overlaps, resulting in a final output of removal_count equals 2. This example highlights that when intervals completely overlap, the algorithm efficiently removes all but one to achieve the desired result. In the third example, we have the input 1, 5, 2, 6, 3, 7, 8, 9. After sorting by end time, the intervals remain in the same order, 1, 5, 2, 6, 3, 7, 8, 9. We initialize preb_end to -infinity and removal_count to 0. The first interval, 1, 5, doesn't overlap with preb_end, so we update preb_end to 5. The next interval, 2, 6, however, starts before 5, indicating an overlap. We increment removal_count to 1. The third interval, 3, 7, also starts before 5, so another overlap occurs, and we increment removal_count to 2. Finally, the last interval, 8, 9, starts after the updated preb_end, so no overlap occurs, and we update preb_end to 9. The final output is removal_count equals 2, meaning two intervals need to be removed. From this example, we see that sorting by end time helps us maximize the number of intervals included, as it prioritizes those that finish earlier. By comparing the start of each interval with preb_end, we efficiently detect overlaps, and the algorithm's complexity remains optimal with O, n log n, for sorting in O, n, for iteration. This ensures we achieve the minimum removals while keeping the intervals non-overlapping. Here, we analyze the time complexity of the algorithm. The first step involves sorting the intervals based on their ending times. Sorting is performed using the sort function with a key, and this operation takes O, n log n, where n is the number of intervals. Once the intervals are sorted, the algorithm iterates through them using a single for loop. Each iteration involves constant time operations such as comparisons, assignments, and increments, contributing O(n) to the time complexity. When we combine these two steps, the total time complexity becomes O(n log n) for sorting plus O(n) for iteration, resulting in an overall complexity of O(n log n). Now, let's consider the space complexity. The algorithm primarily relies on the input list of intervals, which means the input itself contributes O(n) space. Additionally, the sorting process uses Python's timsort algorithm, which has a worst-case space complexity of O(n) for temporary storage. Beyond these, the algorithm uses only a few auxiliary variables such as prev_end and removal_count, which require constant space, or O(1). When we combine all these factors, the total space complexity becomes O(n) for the input storage, O(n) for sorting overhead, and O(1) for auxiliary variables. Therefore, the overall space complexity is O(n). To put this into perspective, consider the brute force approach. A brute force solution would involve generating all possible subsets of intervals to find the maximum number of non-overlapping intervals. This would have a time complexity of O(n*2 to the power of n, as generating subsets takes O(2 to the power of n, and checking overlaps for each subset takes O(n). The space complexity for such an approach would also be O(n), due to recursive calls or storing subsets, making it highly inefficient compared to the optimized solution. The current optimized approach improves significantly by utilizing sorting and a greedy selection strategy to solve the problem efficiently. The time complexity is O(n log n), which is a major improvement over the exponential complexity of O(n*2 to the power of n, seen in the brute force approach. The space complexity is O(n), which matches the input size and is optimal. To break this down further, in the best case, where intervals are already sorted by their ending times, the sorting step becomes nearly linear, reducing to O(n) due to the efficiency of timsort on nearly sorted data. However, in average or worst-case scenarios, where the intervals are unsorted or randomly ordered, the sorting step dominates, and the time complexity remains O(n log n). To solidify our understanding, let's examine the proof of the algorithm's big O complexity. Sorting is the dominant operation because O(n log n grows faster than O(n). As sorting ensures the intervals are processed in the correct order, it is an unavoidable step. The linear iteration through the intervals adds O(n) to the computation, but this is overshadowed by the sorting complexity. Consequently, the overall time complexity remains O(n log n). As for space, the algorithm does not use any additional data structures beyond the input list and the temporary memory required for sorting. This results in a total space complexity of O(n), making the algorithm efficient in both time and space. When solving the non-overlapping intervals problem, there are a few common pitfalls to be aware of. First, one mistake is sorting the intervals by their start time instead of their end time. Sorting by the end time is the correct approach because it ensures we can leave the maximum room for subsequent intervals, which is key to minimizing overlaps. Next, after selecting a non-overlapping interval, it's crucial to update the previous end variable to the end time of the interval you just selected. Failing to do this can result in incorrect comparisons for the remaining intervals. Another common issue is poor handling of edge cases, such as an empty list of intervals or intervals where the start and end times are the same. Neglecting these scenarios can lead to runtime errors or unexpected behavior. Lastly, some solutions mistakenly remove intervals that do not overlap, which is unnecessary. Intervals should only be removed when there's an overlap, so make sure your solution adheres to this logic. Another mistake to avoid is using nested loops, which result in an O(n)² time complexity. Checking all pairs of intervals with brute force may seem straightforward, but it's highly inefficient for larger inputs and often leads to time limit exceeded (TLE) errors. Instead, the greedy algorithm is the optimal choice for this problem. Speaking of the greedy pattern, this problem is a textbook example of its application. By sorting the intervals based on their end times and iterating through them, you can efficiently select non-overlapping intervals. It's important to focus on minimizing the number of removals, rather than maximizing the intervals you keep. During interviews, it's helpful to explicitly discuss edge cases, such as empty inputs or fully overlapping intervals, to show your thoroughness. Additionally, you can make the problem more relatable by drawing parallels to real-world scenarios, like scheduling tasks or booking conference rooms, which can help reinforce the reasoning behind your approach. This problem also connects to several related problems on LeetCode, which can help deepen your understanding of interval-based logic. For instance, LeetCode 452, minimum number of arrows to burst balloons, uses a similar greedy strategy where you sort intervals by their end time. Another example is LeetCode 56, merge intervals, which focuses on merging overlapping intervals instead of removing them. LeetCode 763, partition labels, takes a slightly different approach but still involves a greedy logic and reasoning about intervals. Finally, LeetCode 1024, video stitching, requires selecting intervals to cover a continuous range, showcasing another variation of interval selection problems. Exploring these related problems can help you recognize common patterns and sharpen your problem-solving skills for a variety of scenarios. While the greedy algorithm is the most efficient approach for this problem, it's worth briefly discussing some alternative methods and their trade-offs. One such method is dynamic programming. In this approach, you can use DP to find the maximum number of non-overlapping intervals, but this comes with a higher time complexity of n squared, and a more complex implementation, making it less practical for this specific problem. Another alternative is brute force, where you check all subsets of intervals to identify the one with the fewest removals. However, this approach is extremely inefficient, with an 2 to the power of n time complexity, and is only feasible for very small inputs. Lastly, the sweepline algorithm can be used to track overlapping intervals dynamically. While this method is conceptually interesting, its implementation is more complicated than the greedy approach and doesn't provide significant performance improvements, which is why it's less commonly used in practice for this problem. Great job making it to the end of this walkthrough. To summarize, we used a greedy algorithm to solve the non-overlapping intervals problem efficiently, focusing on sorting intervals by their end times. Remember, greedy strategies are incredibly useful for many optimization problems. Thanks for watching, and don't forget to like and subscribe for more coding insights. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!